welcome back to Van Horn Metz Supplier Highlight Series. I'm AJ Crawford, the Marketing Manager. Today, we're going to take a look at a new hyperdispersant that is optimized for cost and use in general purpose waterborne pigment dispersion applications. We are lucky to have Lubrizol's Performance Coatings Group Technical Market Manager for Hyperdispersants, Jeff Norris. Jeff started his career with Engelhard in their Universal Colorant Development Group before joining Lubrizol in the year 2000. His focus covers specialty additives, including dispersants, rheology, and surface modifiers, and other hyperdispersant technology, where he has worked for 21 years. Jeff, thank you very much for being here today and expanding on your talk from the American Coatings Show.
Thanks, AJ. Great to be here. We are going to talk about waterborne dispersants in general, and in particular, a new product in our portfolio, Solsperse W430. But I'd like first to just do a little bit of review on dispersants in general. So when we have particles that need to be dispersed into a liquid medium or into a continuous phase, it's necessary to have additives or materials that can stabilize the dispersion. Now, in the dispersion process, we start with incorporating the particles in the state as they're received. Usually, they're large agglomerated particles, and they need to be dispersed. That means broken into the primary particle size. This is usually achieved by a wetting and grinding process, basically putting energy into these large agglomerated particles to break them down to the primary particles. Now, those primary particles will re-agglomerate unless we use additives technology to stabilize and keep them separated. And that's essentially the ABCs of dispersant technology, that we have materials that we use, chemicals, in paint coating type formulations to achieve good, stable particle separation and particle dispersion. And when we talk about the fundamentals of a dispersant, we know what makes a material have dispersant properties. In the way that we talk about our dispersant technology, what we call our hyperdispersant technology, we're talking about polymeric materials that have an anchor group, usually with some degree of functionality, that absorbs very strongly to the surface of the pigment or the particle. Now, these can have a single anchor architecture or a multi-anchor architecture. And when we have a multi-anchor type technology, we might refer to that as a comb copolymer. So again, the anchor group providing a strong adsorption to the surface of the pigment, the functionality of the anchor then being matched to this functionality of the pigment or the particle. And then the anchor is attached to stabilizing chains, polymeric chains, either one or multiple. Again, in multiple, we have a comb copolymer type arrangement. And these chains are soluble in the solvent-resin combination, soluble in the continuous phase. And they provide the necessary particle separation to give you the stability that gives a good and permanent type of dispersion stability. In waterborne systems, which we're going to focus on today, there's three types of stabilization. Electrostatic, which is basically charge stabilization. So the additive providing an opposite charge that's on the surface of the particle so that the particles repel each other. This is used widely in waterborne systems. It's not as robust, however, as steric stabilization, what we're going to talk about here, where again, we have polymer chains which are preventing the particles from coming together. In practice in water, we often have a combination of both mechanisms. Electrosteric is what it's called. Some charge stabilization, but mostly steric stabilization. So again, we're talking about the structure of these polymeric dispersants with anchors and stabilizing chains.
Jeff, I have a question for you regarding that. Is there a difference? A lot of times you hear people say surfactant and dispersant. Is there a difference between those two? And now you're adding hyper in front of dispersant. Does that make, like, what does a hyper dispersant differentiate between the three?
Sure, no problem. Those are some great questions. When we're talking about a surfactant versus a polymeric dispersant, there's a couple of differences. And you can say that the structure of the surfactant, as I've described, the structure of the polymeric dispersant and the surfactant, they're very similar in that there can be an anchor and there can be a stabilizing chain. In practice, a surfactant, however, is usually lower molecular weight. And the adsorption of the surfactant on the surface of the particle or at the interface is not permanent. The surfactant tends to exist in an equilibrium phase, which is the one reason why it provides much better wetting, for instance, than a higher molecular weight polymeric material might. And the hyper is sort of a marketing term, if you will, that really focuses on the idea that these are polymeric materials, and the highest technology, higher performing products are actually comb copolymers. So if you want to think about the polymeric dispersants, is that they are surfactants, if you will, on steroids. But they do much more than just what a surfactant normally does, and that provides this permanent dispersion stability.
Great, thank you.
Okay, so following along of that with our anchor chain architecture, the amount of dispersant that we use, of course, is important because we need to absorb the correct dosage of the dispersant on the surface of the particles. Now, and the particles, when they're being dispersed, we're creating surface area, and so there's an optimal surface area for a particle in its fully dispersed phase. And we tend to make recommendations on how much polymeric dispersant to use based on the dispersed surface area of the particle. And this is a data point which is available from most pigment and particle suppliers. The rule of thumb is that the additive on weight of pigment, which we call AOWP, the percent of dispersant necessary on pigment, is derived from taking the pigment surface area and dividing that by 5. So for instance, if you had a surface area of 100 meters squared per gram divided by 5, that we would recommend 20% dispersant on weight of pigment. So we don't make our recommendations based on total formula weight. We make our recommendations based on how much pigment you actually have. And we try to be pretty specific in terms of a starting point. Now, in terms of in practice, we recommend that you do a dispersant demand curve where you make a series of dispersions and you measure viscosity against the dispersant concentration or the particle size versus the dispersant concentration. And we'll often find that the optimal properties correspond with the optimal additive on weight of pigment. That might be a minimum of viscosity, a maximum of color strength, a minimum of particle size. And you can see from this graph, again, where we're plotting viscosity versus the dispersant concentration, that we're going to follow a declining curve or trace of viscosity as we approach, until we approach the optimum additive amount. And then once we pass the optimal additive amount, our viscosity will ultimately begin to increase again. And so there is a sweet spot around our viscosity or our particle size minimum. So we need to have enough dispersant to separate the particles and keep them from temporarily reagglomerating through what we call bridging flocculation. And we don't want to overdose because then we'll have unbound or unanchored dispersant in solution, which will compete with the solvent and then actually drive the particles together and increase our viscosity. The viscosity will not be as high, for instance, or the particle size will not be as large as an undispersed situation, but it's still not ideal. So in these types of situations, just because of the nature of the structures that we're talking about, the chemistry and physics that we're talking about, there is an optimal dosage, and more is not better. Okay, so optimally designed hyperdispersants, high performance polymeric dispersants, they can achieve the highest possible pigment loadings at the minimum viscosity the smallest and narrow, the smallest possible particle size with narrow particle size distribution. That leads us to maximum color strength, highest gloss or transparency, depending on the nature of the particle. And just as important, long-term dispersion, colorant, coating stability. Additionally, since these these polymers have a lot of functionality associated with them, say acid or basic or aromatic type functionality, so that we get strong absorption onto the particle. It's also important that we design these materials so that that functionality is only on the surface of the particle and not available to interact in negative ways or unexpected ways on coating performance. And so when we talk about coating performance, we might say water, sensitivity, corrosion resistance, weatherability, and things like that. So when we optimally design a hyperdispersant, we're looking for maximizing and minimizing the various parameters. Now, there's another design approach that we can use, and this becomes more important depending on your end use applications. So you don't always need the highest performance in every area, but generally speaking, across all applications, you need the parameters that we're showing here. Efficient dispersion across a range of pigments and particles. So we generally don't tend to make dispersants or design dispersants for specific particles. And the range of particles that we work with would be organic pigments, organic colored pigments, carbon black, inorganic pigments, iron oxides, specifically TiO2, and of course, mineral fillers and extenders that may be used on their own or in combination with these various particles. And we're also very interested in dispersants that can disperse mixtures of different types of pigments with different types of functionality. So called more universal type dispersants across pigment particles. We're also extremely interested in compatibility with a wide range of standard resins and solvents and other additives that might be commonly used. And in waterborne systems, we're also including co-solvents and coalescing solvents in these types of systems. Of course, when we're making a good liquid system, we need to have good viscosity and particle size stability. That's sort of a given. And most importantly, when we're not in the highest performing applications, we need to have appropriate cost in use. Applications that sort of fit into that type of definition, where we need good performance but not the highest performance, include in-plant colorants for architectural paints and coatings, say house paints and related type coatings, construction coloration, for instance, colored concrete, stucco or facade finishes, wood finishes and stains, leather and textile coatings, rubber latex, either in natural or synthetic rubber latexes, and for instance, even road marking or striping, so-called traffic paint. So for applications like that, and to fit the definitions of a good fit for purpose dispersant, we've developed a Solsperse W430. And we're going to talk about that in the rest of that product in the rest of our presentation here. It's a 50% active solution of the polymer in water. It's actually a neutralized polymer in that it has a small amount of amine, which achieves a good water solubility. That amine then evaporates as the film cures, which improves the sensitivity in weatherable applications. It's APE, NPE, and NMP free. The only volatile would be that small amount of amine, which is used as a neutralizer. It's effective across a broad range of pigments, as we talked about. That was one of the things that we were looking for, and we designed it to have a wide compatibility with the resin types that are used in those traditional type applications. It can also be used as the sole dispersant in a resin-free grind, so it does not need to be used in combination with a grind resin. Now, most importantly, it does have reduced cost in use compared to industry standard polymeric dispersants. and certainly improved performance compared to typical lower cost or commodity type additives, say like polyacrylates, or even applications where you might use a surfactant, as AJ asked about, in combination with a grind resin like a styrene acrylic grind resin.
Hey, Jeff, for looking at that page there, if it's 50% active, um, in calculating the AOWP, do you need to use more if something's 50% active versus 100% active?
Yes, that's correct. When we calculate AOWP, that's the active dispersant on weight of pigment. So if we did calculate then that we needed 10% AOWP, since W430 is only 50% active, the actual usage as received would be 20%.
Okay, thanks.
Mhm. Okay, and then again, just the physical properties, 50% active. The boiling point is the boiling point of water. We don't have any co-solvents here. And the pH is about 8.5. And that, again, it's a neutralized polymer for good solubility in water. The rest of the presentation really talks about some proof of concept. Looking at the W430 in a range of pigment dispersions, water-based pigment dispersions, evaluated in some off-the-shelf latex paints. So systems that we find work pretty good across a range of applications. So we're comparing the performance to a variety of competitive benchmarks. Now, when we were making inorganic pigment dispersions, TiO2, iron oxides, we're using high-speed dispersion only, just a cowl's blade. And with the harder to disperse the pigments, the organics and the carbon black, we're using a medium milling technique on a paint shaker. We measured our viscosities across a range of shear rates using the TA rheometer. We did measure particle size distribution to make sure we achieved a good sort of off the Hegman scale grind. And then we tended to look at mid-tone type tints at a 1 to 10 pigment to TiO2 ratio. In some cases, we looked at lighter tints. And we're looking at tint strength, of course.
Are you talking like a 6 or 7 Hegman grind?
There's a 7 plus.
Okay.
7 plus to the extent that the pigment particle size will achieve that. And in cases, all of these cases were 7 plus. So yeah, we take it off scale. So we have a variety of starting point formulations we did some work on. This presentation will cover some of these, not all of these. But what I'd like to emphasize here with these starting point formulations is the W430 works with a wide range of industrially important pigments, from the phthalo blues and greens to higher performing quinacridones, azopigments. In most cases, most of the end for the pigments that we would expect this dispersant to be used in, we have found it works quite well across a range of organic pigments, traditional carbon blacks, and inorganics. So we're going to show some examples of the performance. And I've also like to point out here in the starting point formulations that these were water-based resin-free grinds. So we have pigment, water, W430, a small amount of foam control, small amount of biocide. That's all that's in these grinds. It's pigment, basically pigment, water, and dispersant. And we're achieving pretty good pigment loadings. And if you look at the additive on weight of pigment relative to the percent pigment, we are generally following that surface area divided by 5 equation. And you can see that for the most part, the amount of dispersant that's actually being used is fairly modest until we get to the high surface area carbon blacks, like the Special Black 4, for instance, which has a very, very high surface area and because of its much a smaller particle size, does have a higher dispersant demand. But in general, the industrially significant pigments, the dispersant demand is right in keeping with what we would expect. Okay, so in the following slides, we're going to review some of the performance with some of these pigments. And this first slide and the slides to follow, we're going to compare the viscosity of the pigment dispersion as made with the 2-week aging of viscosity. And so if we take the dispersion, put it in the oven for 2 weeks at 50 C, we measure viscosity at room temperature and after aging. And we need to want to say within maybe 10% of the original viscosity. If we have a viscosity increase beyond that, then that's telling us that we're having a pigment flocculation and we have an unstable system. Generally speaking, that's because if we lose the viscosity stability over time, it's because we have not had as strong an anchoring. We do not have that irreversible anchoring of the dispersant to the surface of the pigment. In this case, we're comparing for the same systems, the viscosity at room temperature and age, as well as the particle size, the DV50 particle size, as made when challenged. And in all cases here on the far left, we're going to have Solsperse W430 compared to a variety of industrial significant competitors. All of these are polymeric dispersants. And so you can see some indications where the comparative dispersants did not perform as well as the W430, because we see either gelling or massive viscosity increase. In some cases, we have the viscosity performance, which is better. In many cases, the W430 is outperforming the industry standards. But making a low viscosity and low particle size dispersion is your start. But at the end of the day, what we need to do is to have good color strength. Here we have these tints, the 1 to 10 tints that I described before, in 2 commercially available acrylic latexes. And so here we have W430 always giving us being the control, 100% tint strength, and comparing to the other dispersants, some of which in the past, in the previous work, would have shown perhaps lower viscosity, but also lower tint strength. So across the board, overall, for this particular grade of red iron oxide, and the W430 is a pretty good performer at a very, very reasonable dispersant demand of only 1.25 additive on weight of pigment for a 60% pigment grind.
Disclose the competitors there, but what is the pricing similar across competitors? Are you where would you say, not exact numbers, but where would your pricing fall in comparison, do you think?
Generally speaking, we've selected the W430 for these applications where cost and use is extremely critical, and most of these competitive materials are at the higher end of the performance range. They tend to be universal across the types of pigments. Our cost and use across all of these competitive materials is better. For TiO2, we're making the 75% pigment loading, so we're approaching the pigmentation that you would achieve with a TiO2 slurry. But at 2% additive on weight of pigment, this is a TiO2 dispersion, which is more fully stabilized for long-term stability than a TiO2 slurry. So we're checking here again against the industry standards. The W430 having good viscosity and particle size stability. Most of these dispersants do a pretty good job at achieving the particle size. Not all of them have the good viscosity stability, meaning again that their anchoring perhaps is not as strong. And in this case, we're looking at just putting the TiO2 dispersion into a clear base. And here we see that the W430 is pretty good. Achieving the opacity. You'll see this competitor number 1, in fact, was a little bit better in terms of opacity, but not as good in terms of a slurry viscosity. And so Generally speaking, there's a balance of properties that we're looking for. The cost and use with the W430 is much better than competitor one, which is a more high-performing additive, but is used quite a bit in industrial type applications. For carbon black, we're looking at a variety of different carbon blacks. Here we're looking at the Raven 1035, which is a mid-color type pigment, can be used for mass tones or in tint. We have here nice viscosity stability, most important, not always the lowest particle size or lowest viscosity, but the best viscosity stability. And this is a big challenge when working in carbon black. In terms of the mass tone color, we're doing pretty good. If we look at competitor 4, that was a higher performing dispersant, and so it's a little bit better performance overall than the W430. But across the board, W430 is a competent performer for this system, the 1035 mass tone. But now looking at the 1035 there for a tint application, and to be honest, the 1035 is used as often in a tint application as it is in a mass tone application. The color strength of the W430 is actually a little bit better than the competitor number 4. So we again believe that the W430 is a very, very competent performer for dispersion of carbon black, regardless of the tint level that you're looking at. Phthalo blue can be a challenge, and we see here that the W430 with this blue 15-1, which is sort of a more higher performing type blue, we're achieving our particle size, but the W430 does end up with a slightly higher viscosity than some of the other indications. Certainly a little bit more stable. Color strength is good though. And again, at the end of the day, viscosity could be a little bit higher. Viscosity stability is good. The color strength is right where it needs to be.
From my screen, you color match the bars there nicely.
Yes, in fact, we did. But
Yeah.
Your results may vary, as it turns out.
Right.
Yellow iron oxide can be a challenge. This is a 55% grind at the 15% additive on weighted pigment. You may remember that with the red iron oxide, which is a larger particle size, we had 60% loading, but 1.25 additive on weighted pigment. So we're almost 10 times or more than 10 times higher in the dispersant demand to adequately disperse the yellow iron oxide. So yellow iron oxide can be a sort of a distinguishing pigment when we're looking for dispersant performance. And we're with a competitor number 6 here because this was one of the better performing competitive dispersants. A number of the other dispersants we had looked at with the earlier pigments could not achieve the 55% loading at reasonable viscosities. And if you look, this is pretty low viscosity. So our color strength is right on where it needs to be. Our viscosity was lower and the stability was better. So again, a pigment that's not always easy when you're looking across a range of pigments with a particular dispersant. And then finally, a high-strength organic yellow. When we're talking about yellow pigments that are used quite a bit in architectural systems, this is one of the standards. And the anchor system on the W430 is ideal for a pigment like this. Right up there with maybe our closest competitor, which we list here as competitor number 7 in terms of viscosity, stability, color strength. At the deep level is actually a little bit better, but we perform well. And again, this is another pigment system which can be quite challenging to get a 40% pigment loading. Now, in addition to color strength, in some applications like wood coatings, stain resistance is extremely important. And stain resistance in a waterborne system has a lot to do with the water sensitivity of the additive and polymer system. So the coating system can be designed to be stain resistant, but if we use water-soluble additives, they can have a negative impact on the stain resistance. So standard stains, if you will, that are used in wood coatings include coffee, red wine, and mustard. And in this testing, we're making a white wood coating using our dispersion of the Ti-Pure 706 that contained on total 0.7% of the dispersants that were being used, including the W430. And what we're looking at is the delta E change between the unstained and the stained the coating after the stain has been rubbed off. There's a visual. Really, you can't see much of the stain except in the worst situation. The very, very, nasty mustard. Mustard is the bane of the stain resistance test. You really have to have a really high quality system to avoid mustard. Coffee's not looking too good right there either. But all things considered, considering the structure of the W430, the chemistry that we use, the cost effectiveness, when we compare the W430 to more expensive dispersant architectures, its stain resistance is right up there where it needs to be for consideration in wood coating. And this is an in-use application globally where W430 has actually found a lot of success in wood coatings where stain resistance is important. Being a water-based system, you might always think about, well, what is its contribution to foam? And here we have 1 gram of dispersant into 100 grams of distilled water with shaking. And then we're measuring the foam height in a graduated cylinder. So we create some foam at the start, and then the foam dissipates over time. No defoamer is added here. And so what this shows compared to the other water-soluble polymeric dispersants that we've tested here is that the W430 is a good pigment dispersant that does not support foam. So it does not stabilize foam, which would mean that you'd need to use less anti-foam or defoamer in your system. And this is, of course, always a concern. The fact that W430 does not per se act as a wetting agent and is actually a primary dispersant, this is an indication that you see as a result of the good performance in this foaming test. In summary, we've described W430, which we developed for general purpose water-based coatings and colorants. The focus is on architectural coatings, but there's a variety of other resin-based systems where the W430 finds utility, especially across a wide range of pigments. It has the necessary viscosity reduction and particle size reduction and stability to be a competent performer. You can get the amount of pigment into your dispersion that you're used to or that you require. It is particularly compatible across a wide range of resin chemistries and has good water solubility as well as co-solvent stability. As indicated from the stain resistance, it has a minimal effect on the water sensitivity. The amine neutralization works to achieve that. The amine coming off as the film cures. Chemical resistance is good. Blocking and color rub are exceptional compared to lower molecular weight surfactants. W430 is made in the USA, and compared to other technologies, we have a good supply situation on it. And I think that's probably the last thing I'd like to leave you with. This is a good dispersant to use in 2022. Any other questions, AJ?
You answered my last one. I was going to see how the supply was in the world that we're living in right now. So it's good to see at least it's made in the US and readily available. So for any VHM customers out there or anyone interested, feel free to head to our website, www.vanhornmetz.com, and you can request a sample of the W430 there. Jeff, thank you so much for your time. It was a very interesting presentation and a nice overview across a wide range of pigments. So I appreciate you taking the time.
My pleasure. Thanks a lot.
Thank you.